Welcome to U Waterloo Engineering. My name is Tony, and on behalf of the University of Waterloo rover team, I am proud to introduce you to our 2020 URC Mars rover, WA-E. Over 50 members from more than a dozen disciplines across various faculties have spent the past 7 months designing, building, and programming our 2020 rover. Our team is organized into 5 divisions, being mechanical, electrical, software, science, and business. Over the past month, the team has been busy conducting full system tests and task simulation in environments which are designed to closely mimic the competition.
Our drivetrain features a 4-wheel suspension system, selected for its lightweight, ability to overcome medium-sized obstacles, and ease of maintenance. The rover features 12-inch balloon tires and is able to overcome 16-inch obstacles and has a top speed of 6 miles per hour. The newly designed robotic arm, which has a maximum lifting capacity of 25 pounds, is capable of holding 10 pounds at full extension. We implemented linear actuators and worm-driven joints to reduce backlash. In doing so, a lightened design was created and validated through FEA without compromising on performance. This year's arm has 5 degrees of freedom and a continuous rotation wrist, which interfaces with a new end effector design featuring load sensing capabilities, achieved with a force-sensitive resistor and attachments, such as an Allen key tooltip to simplify task completion. The forearm and wrist assembly features a compact profile and half the weight of last season's design, while the end effector has the same footprint but extends almost 1.5 times as wide. Finally, compared to last season's design, dead shaft joints were used extensively to eliminate the need for keyed shafts on many joints, easing manufacturing, assembly, and maintenance. This season's science module improves upon last year's sample extraction mechanism by creating a more precise soil extraction and deposition mechanism. Instead of an auger, this season's module utilizes a belt-driven shovel system that lifts the collected sample up through a slot in the centrifuge and deposits the sample into one of 8 test tubes. The centrifuge is indexed by a Geneva drive mechanism, with the test tube sealed off using a sealing lid. The samples are initially analyzed via temperature and humidity sensors, which enter the soil sample during the extraction process. Finally, the entire module has a footprint of under 1.5 cubic feet and weighs less than 15 pounds.
This year's electrical design focused on refining our existing designs and improving overall system reliability. Our new electrical box provides greater accessibility to the components contained within, which will no doubt be useful in the heat of the competition. This is enabled by the fact that module-specific boards, ARM and Science, are mounted onto the respective modules rather than in the electrical box itself. A new addition to the rover this year is the safety board, which monitors the various voltage rails of the system, as well as reads the output of 6 current sensors that monitor the current through the motors on the current module.
This year, the team re-architected the rover software from the ground up, with an emphasis on reliability and robustness. We wanted to make sure that the rover's performance across all the tasks were stable and consistent, implementing contingencies as countermeasures to potential system failures.
All of our custom boards are connected on 2 separate CAN networks, running software that will automatically switch to the other network when it detects bus issues. We also had a focus on improving teleoperation controls to make them simpler and more intuitive. Our drivetrain can be controlled through open-loop voltages, closed-loop speeds, or even commanded to maintain a certain position. Our arm can also be controlled in open-loop, closed-loop speed, and closed-loop position modes as well. We're also working on improving our inverse kinematics controls so that the operator can command the arm's end effector position. The operator can quickly cycle through all of these control schemes and choose the one that's most appropriate for the task at hand. Our autonomy software is written within the FlexBee Behavior Engine framework to be able to organize and facilitate the various autonomy routines. Operators can adjust the level of autonomy, which enables them to pause in between the autonomous task legs to enter or adjust GPS coordinates and ensure the system is working properly. The rover navigates to targets based off a simple vector field approach that uses GPS fix and IMU to compare its location in relation to the target. This can be visualized in MapViz to ensure the system works properly. We use open source packages to achieve reliable vision. The vision system was initially tested on a Roomba robotics platform, so we could quickly prototype and iterate on it. This translated well into the rover, where we tested it outdoors in conditions similar to the competition in terms of terrain. Our rover also has access to a Z camera, which provides real-time depth data which can be used for obstacle avoidance. This year's rover features comms running on 900 MHz, 2.4 GHz, and 5 GHz. We have implemented automatic load balancing so that more network traffic goes through the frequencies with higher bandwidths.